All right, in this video, we're going to introduce the two-dimensional curl and divergence of a vector field. And so if I have a vector field f, which is equal to pi plus qj, then the two-dimensional curl, which is written curl of f, is defined to be this quantity partial q partial x minus partial p partial y. And we recognize this, of course, as the integrand in the double integral that appears in Green's theorem. And so what does this quantity measure? Well, it measures the rotation of the vector field f at a point. So if I have a positive curl at a point AB, that's telling us that the vector field f is rotating counterclockwise near that point. So if I think of my vector field as describing, say, fluid flow throughout some region, and I place a little paddle wheel in this body of water at the point AB, then the vector field is going to rotate that wheel counterclockwise. Right now, if the curl is negative, that's telling us that the field is rotating clockwise near the point. And so now we're going to rotate that paddle wheel clockwise here. All right, now if the curl is 0, that's telling us that we're not rotating near the point. And so if I were to place the paddle wheel here, then this vector field is not going to create a rotational tendency, either counterclockwise or clockwise nearby. All right, so now we're going to define a vector field such that the curl vanishes, so in other words, is equal to 0 throughout some region as an irrotational vector field. Okay, so a little side note here. If it is the case that the curl vanishes throughout an entire region, and let's say we know that region is open, connected, and simply connected, then if you recall from section 15.3, this was the criteria for this vector field f to be conservative. So in other words, if the curl vanishes on an entire region that's open, connected, and simply, so it satisfies all those criteria of that test, then we can conclude that the field is conservative. We'll return to this idea in a lot more detail in section 15.5. But for now, let's go ahead and look at the divergence of the field f. So we'll write this as div of f, so divergence of f is defined to be this quantity, partial p partial x plus partial q partial y. And what this quantity measures is what's known as the flux density of the vector field at a point. Okay, so if I have a positive divergence at a point, then we say that the vector field f is acting as a source at this point AB. So here, if I were to draw a little circle centered at that point, then I'm going to see a net outward flux across that circle that's generated by the field. Okay, so stuff is flowing outward from the point, so it's acting as a source here. Now, if the divergence is negative, then we refer to F as a sink at the point AB. And so now we have an attraction as opposed to a repellent. And so we see now a net inward flux nearby this point AB. And lastly, if our divergence is 0, then we say that the vector field is incompressible at the point. And there you have net flux that's equal to 0. Okay, so you could have fluid flowing into this region and out of it, but the net flux, right? So in other words, looking at the positive and the negative contributions, they're going to be equal and opposite across this entire boundary. And so the divergence will be 0. Okay, now a vector field whose divergence vanishes everywhere throughout some region, okay, we call this a source-free field on the region. And this also is referred to as a solenoidal field on that region. That's another term for that. Okay, so in the next video, we'll look at question 5, which has us compute the curl and divergence of a couple different vector fields, and then we'll interpret the results in terms of rotation and flux. So I will see you there. All right, thanks.